Okay. All right. So question says a particle moves along the x-axis so that any time t greater than 0, its position is given by x of t equals t cubed minus 12t plus 5. This may look a little bit odd. X is a function of t. T is time. You'd see this in physics all the time if you take those classes in the future. So question A, when it asks for the velocity is the derivative of position. Is that something you saw in class?
Yeah.
Okay. And that means, in short, you have to be able to take a derivative of this function.
Mm-hmm.
So if x of t is your function, your position function, you have to be able to take a derivative of this.
So it would be like 3t squared minus 12.
Plus 0, or you don't even have to put that. Okay. Well, that was good to hear. That was good that you got the power rule down for derivatives. So some students, and I guess I should change my notation here slightly, x prime of t and v of t are exactly the same here.
Mm-hmm.
Okay. Now acceleration is the derivative of velocity. So part B, acceleration is the derivative of velocity. So a of t is equal to two things. It's either x double prime of t, meaning the second derivative of that, or it's the derivative of velocity. Basically, it's the derivative of this thing here again.
Okay.
And that is 6t.
Yeah.
Okay. All right. Part C, it says to find all values for which the particle is at rest. So at rest has the following meaning. It means that the velocity is equal to 0. So this is the most challenging, one of the most challenging things for an early calculus student is like, which function do they use? Okay. And it's this one, this 3t squared minus 12, because that's the velocity one.
So you just use the first derivative, basically.
Yes, but it's possible that they could give you something where they give you velocity, and you got to know to use that. So you have to solve for t here. Okay. And you should find that t squared equals 4. So t equals plus or minus 2, but t is defined for only positive values.
Only positive 2.
Okay. So t equals 2, and then you got to put a unit on here, seconds. Particle is at rest.
Okay.
Okay. Now I'm gonna just go a little bit beyond what we're doing here, and I'm gonna make a number line for v prime. So v prime is defined from 0 to infinity, and this is not based on this, but at 2, it's at rest.
Okay.
Have you talked about when the particle is velocity is positive or negative? Have you talked about that?
Well, we looked at like those like the particle motion graphs. I don't know if that's what they're called.
Okay.
But I don't know.
All right. Well, let's not do this right now then. So part D is find the speed of the particle when its acceleration is 0. So there's really two parts that we need to figure out when acceleration equals 0. So you have to go use the acceleration function. So that means this 6t. So again, you got to know which one you're grabbing and why. So 6t equals 0 when t equals 0. But again, it's asking for the speed. And speed is another word for velocity. It's actually the absolute value of velocity. Are you taking physics, or have you taken physics?
No.
Okay. All right. Well, your car tells you speed. Velocity depends on direction. So if you were to get a negative number, you would have to take the absolute value of that value. So this is basically saying take t equals 0 and put into the velocity function. Basically find the velocity of 0. So your velocity function is 3t squared minus 12. So your v of 0 is 3 times 0 squared minus 12, which equals minus 12. But since it's asking for speed, you take the absolute value, yeah, of that.
Okay.
All right, is the particle moving toward the origin or away from the origin when t equals 3? Justify your answer. Okay, so at t equals 3, there are 3 values that we can find. We can find the x of t, so its position. We can find its velocity of t, and then its acceleration of t. And this part's kind of a continuation of this number line up here.
Okay.
But so you said that really wasn't clear, so I gotta be careful not to get, because this will be very confusing when we do it. So there's really 3 graphs. So we're gonna graph each of these. Okay, so the first graph there, I'm gonna do it on a calculator. X cubed, what is the function again? Sorry, I lost it. Minus 12t minus 12x plus 5. Okay. Let me snip this in and then we can talk about it. Get a nice reasonable window. All right, let's go 0 to 3. Let's go 4. That'll be a little easier to see. Okay. I think I've got it. Bless you.
Thank you.
Are you like most of us and have horrible allergies here?
Yeah, I've been taking Zyrtec every day.
It's tough. And you're doing golf for a while. It's like even worse to be out on golf courses.
Yeah, exactly.
Okay, so here's the position function. Okay, so this is like saying, and this is, I think it's a little bit unclear because it depends on whether you're looking at position or velocity or acceleration. There's like different rules. So consider the origin here, the x-axis, to be home. I find this is the best analogy to make. We'll see if it works here. So you start out 5 miles from home, because this is position. This is x of t. X of t means position. Here, right here, you are home.
Mhm.
So you were traveling home. You were at a cafe and you drove back to your house, or you were at school, you drove back home. Okay.
Okay.
Here, you are the furthest from home. But you went in a different direction. Like let's say, I don't know, you were at your school, and then this time you're going like, I don't know, downtown. Okay. You were going the other direction.
Mhm.
And then you're coming back, because here you're back home. So it's asking, go ahead.
Where would, so if you're starting at home, basically you're going to your first point and you're going back.
No, you're starting 5 miles away from home.
Oh, okay.
Like at school, for example.
So when it hits the x-axis, that's like home, basically.
Yeah, that's like they call that like your reference position or wherever you started.
Okay.
Even though you didn't start there, it's like relative to where you want to be.
Okay.
The more simple example is like if you had a driveway, when we have straight lines, but you've moved past that. Maybe we'll do an example like that. But here you're back home, like because your distance from home is 0. That's what this means. X of t equals 0.
Okay.
So you have to be in your driveway, more or less. And then you go the other direction, because like this is positive and this is negative. So like it could be, north, south, east, west, it doesn't really matter. But you're going away from home, and you're furthest away from here, because look at this distance here. You're minus 10 away from home.
Okay.
So here, during this period, or this length, you're getting like further away. But then when you go back this way, you're getting closer to home.
Okay.
So at t equals 3 or x equals 3 in this case, which is what it's asking about, do you see that you are moving?
At x equals 3?
Yeah, well, t equals 3. Sorry. So I had to graph this with x. This is really t cubed minus 12t plus 5. When t equals 3, that's really x equals 3 in our graph. It's right here. It's
You're
saying what?
going closer to home.
Yeah. So in this case, towards the origin is because the origin can represent your home.
And so how would you justify your answer with the graph?
Yes.
Okay.
With some of these points. And we should do a simpler graph to make this a little more clear.
Would this be like a calculator question because for the graph, or would you have to know how to make that graph?
It says you can use a graphing calculator on this one. They can make it slightly easier so you don't, so you can still graph it by hand. So,
Right.
but it looks like
Let
this
me
would
see
be.
what he put on his, because this is like what this is, the particle motion. Is that what this is called?
Yes, this is part of that particle motion.
So I think he put if it would be a calculator. Let's see. Oh, it says conceptual is particle motion, velocity, acceleration, etc.
So parts A through D were definitely by hand.
Yeah. Okay.
E kind of required a little bit of this.
Maybe he would just give us the graph.
Sure. Yeah.
Okay.
Would you like to do kind of another example on part E that isn't like this, that's a little bit more straightforward, but incorporates position, velocity, and acceleration?
Sure.
Okay. Right. So we're going to make a graph here. And the first graph we're going to make is position versus time. So try to clarify all this stuff. This is X and T. So you're in your car in your driveway. Okay. And this is gonna be a little bit, this is how you normally do it. You get in your car and you back up. Okay. You back up, right? You go out your driveway.
Mm-hmm.
So let's say your driveway is 100 feet. Okay. And so you back up here. Okay. Now let's just say you wait in your car because somebody waves at you. Are you still 100 feet away when you're at the end of your driveway as you're sitting in your car? Like, are you moving? You're just sitting there.
You're not.
You're not. So you're still like this. And then you realize, oh my goodness, I forgot something. I got to come back. So here you drive back in. So notice you started here and you ended here. Okay, so is the scenario okay?
Yeah.
Okay, now here's your graph of velocity. Yeah, there you go, right there. So here's your graph of velocity and time here. So during this part where you're just sitting in your car at the end of your driveway, do you agree that you're not moving?
Yeah.
So your velocity is 0 there. Okay.
Okay.
But when you backed out, your car had velocity. Now you were moving backwards. So we call backwards negative. And I don't know, let's say you were moving at minus 10 miles per hour out your driveway. Now, does your speedometer show that it's minus 10?
No.
It just shows it's 10, right? So your speedometer, your speed, is the absolute value of velocity. So it doesn't care whether you're going forwards or backwards, right? So you're going here. Now, this line right here is the slope of, let me write it out here. It's the slope of the position.
Okay.
Whatever this slope is, and I just made up numbers. Let's not focus on those. Same thing here. This is very important. The slope here is some negative number because it's going down.
Right.
This v equals 0 is also the slope of the position. Horizontal lines have a slope of 0. Okay. Now you're at the end of your driveway. You realize you got to drive back. You drive forward, right? Back towards the origin. towards your house,
So you're going up?
and you have, so you're going towards the house, but you have positive velocity now, and you have positive velocity like this. And again, it's the slope.
Okay.
So we can actually make some real numbers here. So let's call this 4 and 2.
Isn't like the top one, that's your accelerate? No, one of them is like an acceleration and one of them is like a velocity graph, right?
We can go down here and do acceleration if we want, but it doesn't really apply to this particular situation.
But aren't they two different types of graphs? Aren't they like?
So one leads to the next, leads to the next.
Oh, okay.
So that it's position leads to velocity, and then velocity leads to acceleration.
Okay, gotcha.
So since velocity is the slope of position, acceleration is the slope of velocity.
Okay.
And you have to be very comfortable with this progression, because it factors into chapter 4 when you start doing other things in that there.
Okay.
So what can happen here is you, and I mean, this is, if this were a point of emphasis in a class I was teaching, I would give you graphs, and I would ask you to tell me, well, what's happening here? Okay. All right. So we kind of already did one, but let's do it again here. X of t. So you start here, you go up, you wait, then you drive here, you wait, and then you do this. And so these are 1 unit, so 2, 3, 5, 8, 10. So I would ask you like, what's happening from t equals 0 to t equals 2? Like, could you describe what's going on here?
The particle is going towards the origin?
Yes, exactly. And what's going on from t equals 2 to t equals 3?
It's resting. No,
It's at rest. Well, yeah, it is because the velocity is 0. The velocity is 0 there, but it's at the, that's kind of a velocity thing. You just want to say like it's just at the origin. It's not doing anything.
At the origin. Okay.
How about from t equals 3 to t equals 5? What's going on there?
It's accelerating.
No, don't use that word. Only talk about position.
Oh, it's, I don't know, it's going up.
It's going away. So towards, away. So this one's going back towards.
Oh, away from the origin. Okay.
Yes. And here is it's constant. It's doing nothing. It's idle. And maybe idle is a better word for that. This is idle. Okay.
Okay.
And then what's happening? This is maybe the most interesting. What's happening from t equals 5 to t equals 8? It is idle, but what does that mean physically? Like, it's idle, but where?
Away from the origin.
Right. So I like stories to go along with these. Like this is, I started my day at getting coffee. I went home because I forgot something. I had to run in and get it. Drove to school. My car was at school, and then I drove home.
Okay.
Now, if you don't like the story, that's okay. But this whole like idea of particles at the origins, I mean, it's a little abstract. Like this physically means you're doing nothing. Okay, so now we can look at velocities. Like what are the velocities at these various places? So we can draw a velocity graph. So from t equals 0 to t equals 2, you're going towards the origin. But what is the slope of this line? Is it positive or negative?
Positive.
Positive, right? Rise over run. It's going up and then over. So it's up here somewhere, we'll say. What's the slope of this line from 2 to 3?
0.
0, so it's right there. What's the slope of this line from 3 to 5?
Positive.
And it's the same as the other one, so we can use that. This idle time, what's the slope of it?
0.
0. So that's where you can say things like it's away from the origin and it's at rest or not moving.
Okay.
Okay. Towards, what kind of slope does this have? Positive or negative?
Negative.
Negative. So that looks something like this. So that in this first window here, let me grab a different color. So in this first window here, we can say the following. Call it number one. Number one, you're moving toward the origin. That's the position. And it has positive velocity. Does that make sense? It's moving towards the origin.
Yeah.
That's got positive velocity. Then in the second window, it's at the origin and velocity equals 0. So it means it's like not moving. It's not moving and it's, it's at home. You're in your driveway.
Mhm.
In this third window, it is moving away and it also has positive velocity.
Okay.
And then in this fourth window here, it is it's a distance from the origin. We can that's why it's up here. It's distance from the origin, but then it's not moving. So it's velocity equals 0. And then in that last little window here, window 5, it's moving towards the origin and it has a velocity that is negative. Towards negative velocity. So it's possible to have all of these combinations.
Okay.
And I would expect you to be given some question like that on there. So I've taken enough time covering that. If we should move on to something else, what direction?
So that's kind of all you would see with particle motion, right?
You would be given more questions like these at the beginning. They'll give you an equation and they could ask you really any of these. They could say particles at rest, velocity equals 0, velocity positive, velocity negative.
Okay.
They could say acceleration 0, acceleration positive, acceleration negative. They can really ask you anything.
Okay.
Okay, so I'll just make this comment. Like one of the things that comes out of chapter 3 in almost every calculus book is like, I can give you a function of any kind that I want, and you should be able to take a derivative of it.
Yeah.
Okay, and my concern here is that like they generally teach these in such a way that there's like these nice little steps up, and then they just kind of go really difficult questions. So one of the basic ones is power rule, and you already know how to do that. So do you know how to take a derivative of like x squared e to the x? This is a product rule question.
That's the one where you have to like multiply, so it's like x. So you do like don't you do x squared and then you multiply by the derivative of e to the x, right?
Yeah, now you can also make this kind of table or chart over here to the right. Have you seen that with f or g or u and v? Have you seen that?
Oh yeah, u and v.
You got u's and u and v. Great. I like u and v, but u and v a lot better. Okay, so what you do is you identify that separation between the functions. Okay, and you call one or the other, and then you got to take derivatives of both. So what is the derivative of e to the x?
X. I don't know.
Okay, so if you've got that reference sheet pulled up, I put it in the chat. If you don't, here I'm going to snip it in, but you definitely want to have this hand like while you're studying, just these available.
It's just e to the x.
It's just e to the x. It's the nice one there, so it's e to the x. So then what I recommend doing is writing out the formula. So it's u v prime plus u prime v. There's variations on this, like some do u prime, some switch the order. It doesn't matter, but you're basically matching these with these.
Right. Okay. So it's x squared times e to the x plus 2x times e to the x.
Yes. Okay. Now let's do one that's just slightly more difficult here. Let's
You
go.
just you just leave it like that.
Yep.
Okay.
And you're done. So let's say I give you sine x. I'm sorry. Let me change. Let me just move this over slightly. Let's say I give you sine 2x squared e to the x out front here. So this time your u is e to the x, and this time your v is sine 2x squared. So u prime is still e to the x, but this is the one I'm really interested in. Do you know how to take the derivative of something like this?
We covered it. Do I remember? No.
Okay, so the derivative of sine is cosine. Okay, but this is a chain rule. Do you remember seeing that or talking about that in class?
Chain rule.
This is very important. If you didn't, I don't want to give you this example.
No, I mean we talked about sine and cosine and tangent. So
but not the chain. The chain rule is a continuation of the derivative. I didn't really see it in here, but I mean, I'm shocked that it's not part of this chapter.
What is it?
So you take the derivative of the inside function. You start with the outside, and then you have to keep going inside functions. It doesn't look like you're covering it yet, which is really odd, but that's okay. That's totally okay. So we'll just leave it like that.
Okay.
For me to best help you, would you mind asking your instructor if this is going to be on the exam?
Yeah.
And if it's not, that's great. If it is, we're going to have to work on it pretty hard, because it's a little bit odd until you get used to it. Okay, so then you know how to do these, because these are very basic. You have e to the x cosine x plus sine x e to the x, or e to the x sine x. Okay, so that's the product rule, and I'm sure you've covered the quotient rule.
Yeah.
That's another one you're going to see in this exam. So let's say y equals 3x squared over tangent x. You do the same thing, or you create a u and you create a v.
I'm just looking back through the section, and
Okay.
it doesn't, in the book, it only has like sine x, or it has sine y equals x squared sine x, basically.
Yeah, I'm seeing that also, and in the notes you sent me. So I'm not like,
that's the section it would be in, because that's, I think 3.5 is when we covered sine and cosine and all that. So
okay.
probably no.
Yeah, I don't think it is on here. It is really important for this class, but maybe your instructor is choosing to cover it like after this exam, like to do more derivative stuff. Okay. Okay, so so this one here, this quotient rule, I gotta make sure you can do at least one of these. It's u over bv, and this is the one that most students tend to forget.
Minus, right? Yeah.
Yeah, and the order is important here.
Yeah. Okay, so it's 3 tan x times 6x minus 3x squared secant squared x all over tan squared x.
Yeah.
Okay.
Now on the more sophisticated ones that are quotient rule, you end up having to do a lot of simplification. And this is an important thing to ask your instructors, like, do I need to simplify? Sometimes they actually say it on the exam. They say, do not simplify. It doesn't affect this one, like this one's done, but there are questions where like you can do some things, and it creates extra algebra that's, burdensome on an exam.
Mm-hmm. So you move the 6x in front of the tangent, right? Is that
By convention, yeah, because it's possible that it like mixes in with the trig function.
Okay.
All right, so your instructor said here in one of these examples, they were like, find the derivative of, let's just say, cotangent of x, but use the quotient rule.
Oh yeah.
And this is a matter of like remembering what cotangent is. First of all, cotangent is cosine x over sine x. So if you don't remember those, you grab a trig reference sheet and just there's only 6 reciprocals that you need to know, but you need to know. So the u and the v, u is cosine x and v is sine x. U prime, the derivative of cosine is minus sine x. Very important to remember that negative. It's often forgotten. Derivative of sine is cosine. So vu prime minus uv prime over v squared. I like to write the formula every time. That way it's there, constantly remembering it.
So then it's sine x negative sine x minus cosine x cosine x sine squared x. So then do the cosine, like, since it's negative sine and it's cosine and cosine, that does something, right?
It does here. So the first thing is to multiply this out. So it becomes minus sine squared x minus cosine squared x over sine squared x. Because you're a really good trig student, you probably remember this: sine squared x plus cosine squared x equals 1. There's 3 trig identities that could come up. So again, it might be worth again looking at that. This is the most commonly used one. And you might be saying, well, hi Matthew, that doesn't seem to apply here. Well, it doesn't until you factor out a negative in the numerator.
We'll do the, oh,
You don't want to cancel. Like, you can try
okay.
to do
I was
that,
just
but
gonna ask.
you can try. Okay, so this all over sine squared x. Okay, so this part up top becomes 1. This is equal to 1. So it's negative 1 over sine squared x. And again, there's 6 reciprocal properties. So this becomes negative cosecant squared x. And if you go to that reference sheet I sent you, the derivative of cotangent is minus cosecant squared x.
So it's
like that confirms it. Like, so we start out with cotangent x and we got that.
I see. Okay.
Yeah. So you're gonna get a question like that that says prove.
But like,
show.
so if they didn't say like prove it, like you just like know that cosine.
Yeah.
Okay.
Yes, but a good instructor wouldn't give you one that's like.
Well, right, but okay.
Do you have a good instructor? You don't have to answer that. So let's do just one more of these. I'll have you do it. If you look at the reference sheet, you can see that the derivative of let's do, yeah, that was actually, that was kind of a nice one there. We might as well we'll do so we know the derivative of secant of x. We know from this table it becomes secant x tangent x. But it would your question would say to show this, and it might even hint, say, the quotient rule.
Okay.
You might be thinking, well, how do I use the quotient rule here? Well, this is 1 over cosine x. And as odd as it may seem, you do set u equal to 1 and v equal to cosine x. So what is the derivative of 1 of a constant?
Itself.
That is, so derivative of a constant, I'll just snipping it. It is always 0.
Wait, so did you start with what? You started with y secant x?
Yes.
And
Like the question would say to prove or show that the derivative of secant x is secant tangent.
then you know that, how did you get the 1 over cosine?
This is one of those 6 reciprocal trig
Okay.
functions that is just really important to know.
Okay, gotcha. And then the derivative of cosine x is negative sine x.
Yes. Okay. Okay. So the again, like try the quotient rule with this. I'll be right back in 30 seconds or less.
Okay.
And oh, I'm sorry, we didn't cover this. The derivative of a constant is always 0.
Okay. Oh wait, okay. So it's 0 times co.
I would recommend writing it out and not trying to simplify until you get a little stronger in the class with doing this.
Is it? Okay, yeah, I read it. I just wanted to make sure I wrote it right.
Yeah, so you'll see this first part cancels, and this is where I think it gets a little confusing because your answer is sine x over cosine squared x. And what are we supposed to get? We're supposed to get this right here.
How'd you go from that to sine x over cosine squared x? Does that just the 0 that cancels out because it's multiplying by 0? So
yeah, that goes to 0. So the only thing that's left is
got it. So
is
then,
this part.
okay.
So the derivative here, like these are the same, but they're not the same. So actually in your trig class, you had a question like this, where it was like, show that this equals this. And one of the things is to separate out the cosine squareds. So this is sine x over cosine x times cosine x.
Okay.
And I can just decide to put a 1 up here because that doesn't affect anything.
Oh,
so do you see now how this
so the well, I still don't see how you get secant x and tangent x from that.
so sine over cosine is tangent.
Oh yeah.
And then 1 over cosine is
Yeah.
secant.
Oh, okay. That's weird. All right.
Now that's a very reasonable test question to be given.
So it's basically just like, that we just say like prove. Okay.
So is that okay? Is that clear?
Yeah.
Great,
Yeah.
great. Okay. All right. So let's just make a, if you're okay with that, I would like to just look at together the what you sent here. Question 68 is one that is very important in the assignment that we have a really good understanding of how to do.
Okay.
And it's I think it's a good question because it's very it's very conceptual. So we should definitely start with something like this next time. We can maybe do a little bit here, but your test is on Wednesday.
Mhm. I think also next time if we could go over like 53, 54, and this like 55 to 58 section kind of.
Are those the piecewise ones?
Yeah, that's like, and that's the only question I got wrong in the last quiz, like the
Okay.
continuous differentiable, that kind of stuff.
Okay, so there's this yeah, let me snip that in here. There's this really important like progression. So I'll leave you with the following is that if it's differentiable, that means it's continuous. This is always true. If it's continuous, sometimes it's differentiable.
Right.
And you already know about a few of these. There's this one. There's this one. So this is a cusp. This is a corner. Okay.
And tangent isn't there too?
Tangent. Tangents are okay. A vertical tangent, I guess, is the one you probably meant there. Vertical tangent. So this one's interesting because this,
yeah, vertical tangent.
This one's actually not a function. Well, I shouldn't say that. That's not true. Let me not say that. Sorry.
You said label each point as cusp, corner, jump, full, or vertical tangent.
So a jump, so these are all continuous.
Okay.
Okay. And then you get to some that are not continuous. And those were the ones you were dealing with in the last chapter. So the not continuous, you have a hole. You have a jump. And these also have problems. None of these are differentiable at that point.
Okay.
These are never differentiable. But you got to be clear, it's at this particular point. And then the last one is the asymptotes.
Right. Okay. And then for the like corner cusp and stuff, it's like the same, like the cusp is like 2/3, right? Or something like that.
Yeah, you can get these in a variety of ways. I guess I just wanted to give you kind of an overview or overarching kind of thing. But this top one's really important. If it is differentiable, you get the continuous, but just because something's continuous you don't get the differentiable.
Right.
Sometimes. So, all right. Well, this is a great place for us to stop. Thanks so much for scheduling. You actually made my Friday night pretty exciting because I saw a bunch of lessons come in. So thank you. I'm glad to help. And I'll send you the notes and the screen recording out shortly.
Okay. Thank you.
You're welcome. Bye now.
Bye.